Before we get into the normal stuff in chapter 5, we need to talk about rounding and error measurements in general. To do this, we need to talk about significant figures. Before we do that, presently you've been rounding to a specified place value, like a whole number, the hundredth place, or like 3 decimal places, etc. There's two differences between rounding. For addition and subtraction, for significant figures, we always round to the least places in the decimal. So for this first problem, we have 7.245, we have 0.245, we have 3 places there. And we have 455.6, we have 1 place there, which means our answer should be rounded to 1 place because 1 place is the least amount of places past the decimal. We round to the 8th place, we look at the 4, that's not 5 or greater, so we just drop it. And the correct answer would be 462.8. That's because in our error measurements, we only know to an accuracy of the 10th place. That's why we're rounding it to that place. Very commonly used in real world situations where error is very important. Okay, the next one, very similar. We have 3307.123 places there, and 3.123, 123, there's 6 places there. So 4 is the least number of places. So we're going to count to 1, 2, 3, 4 places. We're going to round to this place. Look at the next one that is 5 or greater. So we're going to add 1 and then drop it. So we would say 3304.2939. That would be a more accurate answer. Next one's very similar. We have 1 decimal place, 1 decimal place, no decimal places here, which means we round to the whole number. We have to round to the whole number here. Is that 5 or greater? It is, so we're going to add 1 and cancel it. So 23 will be the correct answer there. Now, a lot of times in these types of problems, you'll be given the place to round to. So you always follow what the problem states. If there isn't anything given, that's when you should fall back on these rules. A lot of the times, however, significant figures will be set, or significant digits also. Significant digits will be said in the problem to round to. And that's typically when you're doing longer multiplication division type problems. Generally, every other problem we use the second rule for, which is you always round to the number of significant digits in the given problem. There's a few rules for knowing what digits are significant or not. The first rule is any non-zero number is significant. So we have 1, 2, 3, 4, 5, 6, 7, 8 significant figures here, sig figs. And there's 8 in that problem, which means as long as every number had at least 8, we would solve to 8 significant figures in the very end of the problem. The next rule is that any zero is significant if it is between 2 non-zero numbers. This 0 here is between 2 non-zero numbers, therefore it is also significant, meaning there's 3 significant figures in 302. In 30,002, there are 1, 2, 3, 4, 5 significant figures. All of the zeros are significant because they are in between 2 non-zero numbers. The 3 and the 2 still count. A 0 to the right of a number is only significant if the decimal is placed. So in 102,000, there are 1, 2, 3 sig figs. The 0 counts because it's in between 2 non-zero numbers. But all of these zeros do not count as sig figs. They're only there to show that we're not talking about 102, we're talking about 102,000. It's a place value idea. So there's only 3 significant figures in this number. Again, any zero that's just to the right of the number without a decimal point, then it no longer they are no longer significant. For this next one, this is also the 102,000, but you see this decimal point is placed. Therefore, all of them count. So there are 7 significant figures. Now, why is that the case? Why is there a difference? If the decimal point is written there, that means we have measured to this accuracy. We've measured to the 10th place accuracy, and the number is actually 102,000, with zeros, all that. It's not 102,012. Like, it's not 123.1, right? It's not this. We've measured it, and this is the measurement we got to that accuracy. So all of those numbers are significant. Okay. The next rule is any zero to the left of the first non-zero number, any of the zeros are not significant. Now, this is the same kind of idea as this one. That these zeros here are place values. They're adjusting the kind of like they're adjusting the magnitude of the number. This number does not equal 102. It's 102,000. Well, the same thing is true here, right? This number does not equal 2,304. These first 3 zeros are there to adjust the number so that it's a smaller number. But that's all they're there for. They are not significant. And so we have 1, 2, 3, 4 sig figs in this number here. The zero counts that's in between the 3 and the 4 because it's in between 2 significant digits, 2 non-zero numbers, I should say. But any zero to the left of the first non-zero number is never significant. You can see this extremely true when you look at this number here, right? 00981. This is the same thing as just saying 981. Those zeros don't actually mean anything. They're just a placeholder saying there's nothing in the 10,000, the 1,000 and the 10,000 place value of the numbers. So that's the reason why you can just drop them and you have the exact same number. Now that's not true when we're talking about decimal numbers, right? We can't just drop them, right? That's what I just showed here. We can't just drop them and say 2003. No, we have to have them in there. However, they do not give us any extra information. It's not like an accuracy measurement to a certain place past. No, it's just that small of a number. So 00981 is the same thing as 981, which means there's 3 significant figures. Okay, now let's do some problems with this knowledge of these 4 kind of rules that we had. Again, the first one is any non-zero number is significant. Any zero is significant if it is between non-zero numbers. A zero to the right of a number is only significant if the decimal point is written. And the last one is any zero to the left of the first non-zero number is not significant. Now we can look at these problems and round to the nearest significant figure. Now you always round to the significant figures in the answer that has the least in the problem. So for instance, in this first one, 30 feet and 50 feet, well, this 0 is just a placeholder. It is not significant. The same thing with this 0. That means we can only round to 1 significant figure. I'm going to do sig fig. That's because 30 and 50 only have 1 in both of them, and 1's the least, right? So our numbers can be rounded to 1 significant figure. Now, as a side note, we also have feet times feet. And feet times feet, this works the same way as our number system, right? If I had 4 times 4, this is the same thing as saying 4 squared. 4 squared, of course, is 16. We can evaluate that. However, with units, we cannot evaluate it. We can, however, say it's feet squared, which is the same thing as square foot, and that's an area measurement. The same thing is true, right? If we have 3 of them, just like if we had 4 times 4 times 4, this would be 4 cubed. Feet, foot times foot times foot is foot cubed. This is also a cube foot, or a cubic foot, which is a measurement of volume. So we can do that with any unit we want. That's going to be important for the rest of chapter 5 when we do unit conversions. Okay, back to our problem. 30 feet times 50 feet is 150. Foot times foot is foot squared, or square foot, whatever makes sense to you. And we have to round a number to one significant figure. You always count from the left to right, so we're going this way. We have one place right here, and we can stop because we need to round to only one place. So we have to round to this place. Okay, the next one, is this 5 or greater? Yes, it is. We add 1. That becomes 2. Now, these zeros, let me clean this up here. These places here must be filled with zeros because we can't just drop it, right? If we dropped it, then it would be 2. But that's not what the number is, right? The number is closer to 200 than 2. And in fact, we round up to 200 feet squared. These zeros are very important to know that we're not talking about 2 or 20. We're talking about 200. That's the place value of idea of our number system. And this only has 1 sig fig here, so we have rounded it correctly. 200 feet squared. That's the issue with having accuracy measurements, is that if you do not have a very good accuracy measurement, 150 must become 200, which is a terrible rounding system. You need to have a more accurate numbers that you start with, because you want to have a better accuracy in your final answer. Okay, for the next one, 3.8 times 2.807. If you do that, you see we get 10.6666. That's on a calculator. That's what it would give you. However, we need to round to significant digits. Let's see how many we have in the problem. So in the first one, 3.8, we have 2 significant digits. In the next one, we have 1, 2, 3, 4. So we have 2 and 4. And of course, we round to the least significant digit. So we round to 2 sig figs. It's going to be 1, 2. We round to this whole number place. We're looking at the next one. Is that 5 or greater? Yes, it is. Add 1. And then we always drop the decimal point if there's nothing in there. And in this case, we get 11. So 11 is our answer there. 200 feet squared was our answer in the previous one. Okay, next one. How many significant digits do we have? Well, we have 2, 2, and 2. So we're going to round to 2 significant digits in our answer. 3.4 times 1.4 times 7.3. If you do that, you get 34.748. And foot times foot times foot is foot cubed. And we round to 2 significant digits. We have 1, 2. We're going to round to this place here. Look at the next one, 5 or greater. Yes, it is. Add 1, and then you drop a decimal part, giving us 35 feet cubed. Okay, last one. We have 1, 2, 3 significant digits, and here we have 1, 2 significant digits. So we're going to round to 2 sig figs in our final answer. Now, doing the division here, we get 60.370, and it continues that pattern on indefinitely. but we're rounding to two significant figures. So we round 1, 2 places, rounding to this place. Look at the next one, that's not 5 or greater, so we just drop that whole part. And we get 60, and this is miles divided by hour, which is the same thing in our English system as mph, which is miles per hour, because it's a very commonly used unit, so we have a shorter hand for it. But it's the same thing. Both of these are the exact same. Now 60, how I wrote it presently does not have two significant digits. It only has one, the 6. But we do have 2 places of accuracy. There's a couple ways we can write this out. The way I would have told you would be to put a decimal point there, but you never just see a decimal point written. When you run around to a certain place, what you can do is say this 0 is significant by placing a bar above it. The bar says we've rounded to this place of accuracy, so we know that's a 0. In fact, it's not a 1, a 2, a 3. It's not anything but a 0. The same thing is true if I were to say 1. Let me do 8, 4, 7, 0, 0, 0, 0. And I were to say I rounded to this place right here. What I'm doing is that this bar says this place is significant. You're making it significant, which means this number here, which is 8,470,000, this number has 1, 2, 3. This is significant, therefore this is as well. Therefore we have 5 sig figs here. And you can use that bar to designate a certain accuracy place. Now in practice you do not see this if all. I don't know if I've ever seen it, people actually using that in practice. Typically you want to round as far as numbers you have that you care about, right? These non-zero numbers is what you're trying to make sure you have. But that's the notation you would write it as if you had a bunch of zeros, like I did here with this problem that I made up. That would be a good place to use that notation.